Hello, everyone, and thank you for coming. So today I'm going to be talking about Andromeda Galaxy, but probably not in the Spark way. So because I want to give you a little bit of introduction about what Andromeda Galaxy is, and you probably know more Spark than I do. So let's jump right in. So I work for SharkNet. SharkNet sounds like sharks, and you could see, well, it's a network of sharks trying to get some HPC done. So in reality, it's a really complex name, something like Shared Hierarchical Academic Research Network. And we're a consortium of 18 Ontario academic institutions, so we're mainly an academic environment thing. And I'm based at the University of Western Ontario, and it's led by the University of Western Ontario. So this is part of Compute Canada, which is the national institution that oversees the funding and distribution of equipment, so mainly HPC. And we have sysadmins and HPC specialists, in total about 20. And this is the map that we have in Ontario. So I'm basically here, but you see Ontario is big. And so what do we do in reality? So we provide services and support to all SharkNet researchers in mainly high-performance, I didn't do anything, high-performance computing. Researchers are part of universities across Ontario, but also from Canada. And we're starting to provide service for large data needs. So in this case, data processing with the Spark, Hadoop, and doing some data mining and machine learning. So that's basically my position now. Here you see we mainly do compute, but also for some reason it doesn't want to. High performance, and we do virtual machine, cores, storage, clustering. So, but what's up with Andromeda Galaxy? What it is? So it's known as M31 or Messier 31. It's a spiral galaxy, and as you can see here, and if this thing is not playing with me, so you see the center here, and then you see kind of a spiral thing. So this spiral is actually some arms. I'm going to talk a little bit more about that in a bit. It's the closest galaxies that we know of, and it's bigger than our own galaxy. So those points is kind of, okay, well, that's Andromeda Galaxy, and then what? Why Andromeda Galaxy? Because it looks cool if you have a Mac, for example, as a wallpaper, or even if you don't have a Mac, you can have a wallpaper and it's really cool. And as a t-shirt, you could have a t-shirt and it's cool. Also mugs, but what about science? Is it cool for science or not? So yeah, so what do we know in science? It has a little bit of 1 trillion stars, so it could be cool to analyze all the stars in one set, so we can use Spark for that. It's 2.5 times longer than our galaxy, so before I said it's a little bit larger, but how large it is. So to have merged with another galaxy, so basically at some point there was 2 galaxies and they collided, and now it's a really big galaxy. Now we know it as Andromeda Galaxy. It has 26 known black holes, and black hole is something that everyone likes. And can be used as a galaxy laboratory, so for extragalactic astronomy. So because we have our own galaxy, but what's up with the next galaxy or the rest of the galaxies? Is it the same, or is it the same what we have here, or is different the physics in general? And it will collide with us eventually in 4 billion years. So probably we are not going to be here for sure, but it will. And we're going to have to find another place where to live. And as you can see here, there is, again, a wallpaper of Andromeda Galaxy, which looks really cool. But why Andromeda, again? So that doesn't answer, and it may not answer the question, why Andromeda? But imagine that you live in really small world here, and you live in a house, and for some reason you cannot go outside. When you're a child, for example, so you may not be able to get outside. So the only thing that you can do is take a look at your neighborhood using your window, and then you may be able to see how big your neighborhood is, or the color of your house, based on the house next to it or something like that. You could even check the features of the house, or you could infer the feature of the outside of your house by looking at different houses. In the case of our own galaxy, we cannot just go outside of our galaxy. For example, here's our galaxy, and this is just a cartoon, basically. So we live around here, so we cannot go outside, take a picture, and say, okay, this is our galaxy. It's too far. So what we can do is take a look at another galaxy, or other galaxies, and say, well, based on what I can see, I can infer some structure or internal structures of our own galaxy. And what we see is that it has some kind of a globe or so, which is called the bulge. There is kind of a disk, which is something like you see here, some arms where some star formation is happening, and the star formation gives us something like the sun, some planets. We live there, so we like the star formation, and of course we like the arms because we live there. So, and then the extension, how extended it is, well, we don't know that yet, but we can infer depending on the other galaxies. And you see that there are some other things like the halo. The halo is it's a huge circle surrounding all the galaxy, and inside the halo there is some kind of globular cluster outside of the main disk and the main core or bulge. So particularly, we are interested in taking a look at Andromeda because it's an external galaxy, and we know that here's Andromeda, but we don't know the extension yet. So we say, well, probably here's the end of the, but remember, this is gas, so it doesn't stop here and then say, okay, here's the hard end, and that's it. It could extend more or less, but we don't know, depending on the gravitational bound that we have. So now we say, let's take a look at this area, this area, this area, and this area, and see if some of those sources actually belong to the galaxy, so we can know the extension of the galaxy and infer our own extension of the galaxy, how extended our Milky Way is. So, and that was done by Ravandi et al., 2016. So they took some pictures around here, and now the problem is, you take pictures, and the picture that you take, it's 2D. It's not 3D that you can say, well, this source is not part of the galaxy. It's foreground, it's background, because you're taking a 2D picture. So imagine that you're taking a 2D picture of, let's say, Boston, and at some point really far, you don't know if that building is part of another building, or it's in front, or it's back of the building, because that's too far, and it's what happens here. And okay, so is this extended Andromeda? What can we do? How can we analyze it? Okay, so first we have to take the picture. How to take the picture? So you can take the picture, in this case with a Spitzer IRAG telescope. It's an infrared telescope, and what does it means that in general you take an optical picture, for example a photo, it's an optical. But in infrared, you're going to see something different. For example, this is the optical Andromeda Galaxy. So this is what you see. And infrared, you're going to see something different. It's another picture with a different wavelength. And if you take in infrared plus X-ray, you're going to see something different. If you take only X-rays, so you're going to see this. And you may think this is not Andromeda Galaxy, because I remember the Andromeda Galaxy like this. But it's because you're taking in a different wavelength. So now, the problem is how to actually, from what we know, we can compare different wavelengths or different catalogs or different pictures with another, so we can understand what's happening with Andromeda Galaxy. Because you take this picture and you don't see the same. You take this picture and you see some extension a little bit different, and it's the same with infrared. So they detected that there were over 4,000 sources in that little plate that they took. And that was the extension of the disk and halo, something that I explained before. So the disk is something extended, and the halo is something really as a sphere enveloping the whole galaxy. Now, why do we want to classify them? So first, to know the extension, as I mentioned before. But really, all those over 400,000 sources belong to Andromeda? Well, we don't know yet. And can we use different catalogs, let's say something that we already know, to classify the sources and then say, well, yes, this source is known for this, or it's a black hole, or it's something different. So for example, here's a cool picture of a black hole, and then, or could be another galaxy, or maybe a planetary nebula. So some really nice sources. And what can we learn about these new objects? If they are not known, can we classify them? Can we say something about these new objects? As we know, so we don't know the whole universe. And you can say, well, this is a black hole, but what if we find something different, a different source that we didn't know before? So that's the point. So which catalogs? So already there is SIMBAD, there is NET. SIMBAD in that region, because SIMBAD it's a huge catalog, it has, I think it's like 1 billion sources or so in all the history. But in that particular area, so SIMBAD has roughly 4,000 sources, and NET has over 100,000 sources. But MAST, another catalog, so this is the MISC archive for the Space Telescope, and it has also some different wavelengths, as I mentioned before, so different pictures. It has over 118 million sources, but this is only in that area again. So the whole catalog is bigger, and at some point it would be great if we can analyze all the sources and could classify or even find different sources or different objects like planets or something else. And so SIMBAD, NET, and MAST, they have some infrared sources, some optical sources, and some UV sources mixed together. So we have to find a way, as I mentioned before, the pictures that we have, that we could match the pictures, one infrared, one optical, and one UV. Then we can compare them. And how? In reality is that a Spitzer has this resolution, and this is at 3.6 microns, so you see here. And the Hubble Space Telescope, which is more optical, but this part is infrared, and this is almost the top of the infrared that the Hubble Space Telescope has, is 1.1 microns. I think the top is 1.6. And so you see, here's one source, and it's there in the Spitzer, and this is another source, and it's there, and so on. So you see, so it's hard to actually measure, even if we know these sources, because we know these 5 sources to be some really nice stars. I'm not touching anything. So here's one, and here's another. Okay, and this is one, and this is another. But really, can you see the difference? And can you say, well, yeah, those 2 dots are actually the same. And I'm sure they are the same, and it's a black hole, for example. So it's actually really hard. And the only way to kind of define the distance and in the space, it's using arc seconds. And that's going to be a kind of the way, it's similar to, it's an angular measurement, not a linear measurement like miles or kilometers. But we're going to say that at 2 arc seconds, that's going to be a good match. And we're going to see that this dot with the other dot are going to be the same. That's the first assumption. And now we jump with, okay, so we have a spark, plus we have Andromeda Galaxy, so we can use from a spark the key values. We can use some declination and right ascension. Those are basically the coordinates, talking about longitude and altitude. And well, we don't have really altitude, but we have longitude and altitude. We have the observations, could be the other part. So then based on what we have there, we can use some joins, probably group by key, filtering maps, and sort by key, depending on particular the coordinate of that star. So we have the coordinate, so we have another star around. So we want to see if they are within 2 arc seconds, or we can say some there are a lot of miles, but so if they are close to each other, they are going to be the same, because taking the resolution or even taking the pictures, so it's hard to match between one wavelength to another wavelength, in this case infrared or optical. And at the end, our hope is to get the classification of all the IRAC catalog. So the over 400,000 sources would be classified. Okay, based on that, we have the declination and we have the right ascension. So the right ascension here, declination, as I said, they are coordinates, so basically points in the space. And net plus SIMBAD plus the IRAC catalog. So the IRAC catalog is the one that we want to classify. This is new, and we want to say if, based on what we know before, the IRAC catalog can be classified. So you see some points now, and then, okay, based on net plus SIMBAD, which they have the same, or they should have almost the same, now we can classify the IRAC catalogs. Okay, now I have some UV stars, and I have some globular clusters, and you see the colors. For example, stars or UV stars are just the red dots here. We have galaxies, here the pink one. Of course, a galaxy doesn't belong to the galaxy. So you don't have a galaxy inside another galaxy. Could be foreground, could be here, or could be background, could be outside. Or could be a satellite. A satellite galaxy, something that is rotating around the galaxy, the Andromeda Galaxy, but it's not part of the galaxy. And okay, we know that, but what about the globular clusters or the X-ray sources? So they could be part of the galaxy. Well, now we have to do some count, and okay, let's count. That is a nice picture, but so we have 613 stars, 70 globular clusters, 63 X-ray sources, 62 galaxies, 52 star clusters. Note this, there is some difference, in astronomy there is some difference about globular clusters and star clusters, but I'm not going to jump in the details for now. Okay, total sources, or known sources, is over 1,000 sources. But I say we had more than 400,000 sources. So what's with the rest? So yeah, the rest, and this is again Andromeda Galaxy, taking a picture from farther away. So it could be some extension here, but, and what about the rest? They are not part of SIMBAD or NET or MAST. And what about other catalogs? So can we use other catalogs, astronomical catalogs, and then in order to classify them? Can we classify them? Is it possible or physically impossible? Because we also have to take into account some physical features in order to classify them. It's not just in machine learning. You can say, well, there's those two dots, and they kind of look like the same. But in reality, you have some velocity, or it's moving towards something, some different places. And that's something physical that you have to take into account in order to say, well, it's part of the galaxy, or it's going further away the galaxy, or it's going inwards the galaxy. Can we use machine learning? Yes, we can use machine learning for some of the parts. And I'm pretty sure we can classify them, but probably we cannot use other catalogs. So in conclusion, okay, so we have the MAST. So what happened with the MAST? I say something about MAST catalog. So the problem with the MAST catalog was that it has a higher resolution. So we have a dot here, and then you say, well, this is the IRAC, and I had like 100 points around. So it was almost impossible to know if this point, with the 100 rest for MAST, which one to choose from MAST. So it could be 100. They were within 2 arc seconds. And even if you go down, let's say 1 arc second, so even 0.5 arc seconds, it was even shorter than that. You still had many sources around. So resolution were completely different. Unfortunately, that's one of the problems with observational astronomy, that, okay, you took a picture, and you cannot have a really high resolution picture because it's really further away. And as I mentioned, or probably I didn't say quite well, but Andromeda is 2.5 million light years away. So if you take let's say some light and you send it, it's going to take roughly 2.5 million years to reach Andromeda Galaxy, and then 2.5 million years to return. So it's a lot of time. So only over 1,000 known sources from a match between NET plus SIMBAD, and we could classify from either catalog. And the rest could be classified using machine learning. In fact, we could try to use what we know from the sources, although it's still 1,000 sources, but we can still check or even do some clustering, let's say a k-means or something similar. So try to see if we can cluster some sources, and based on the physical parameters, we can infer if those sources, let's say they are X-ray sources, or they are just simple stars, or they could be even planets around something different. And of course, as always, we need more data, and probably in order to do better classification. And yeah, so that's my conclusion. So any questions? And of course, I want to thank to my collaborator, Professor Pauline Barbie from the Department of Physics. And some of the photos were taken from NASA and ESO, and I'm sure I'm not doing anything. I'm not even touching anything. Okay.
So you said that when you take the images, you only have two-dimensional surfaces. Have you ever thought about using spectrum redshift?
That's another thing. Redshift, we don't have the redshift, unfortunately, in the infrared data. We have only fluxes and we have visual images. So, but yes, another feature would be redshift to see if it's actually moving from, definitely. Also separate galaxies from, yeah, definitely. Yes? So you mean the extension? So you know that the extension goes mainly 5 degrees or so between the center of the galaxy. So it was between 6 and 8 in extension to the disk and also to that part of it. Mm-hmm. Yes? Sorry, I can. The significance, well, that depends if they are actually in the center of the galaxy or not. But the pictures that we had, they were not in the center of the galaxy. But having some X-ray sources in the center of the galaxy could be that they are old in the population. And given the different population in Andromeda, so it would be nice to see the star formation around. That's going to be something. Yeah, sorry.
You said you had a larger catalog. How big is the entire catalog?
So the SIMBAD and the NET catalog, the SIMBAD is, I think it's over 1 billion sources, and you have to choose just a region around the object or the source that you're taking a look. NET is also like a 1 billion or so. The mass is bigger because even in the region on only Andromeda, it's over 100 million. So I think the big catalog is closer to 1 trillion of stars or so. Yeah. We don't know everything. We just take the pictures and try to recognize something. But reality is that you don't even know if the point that you're taking there is actually a source. Could be something different. Could be an error when you are getting the pixel in the photo. Okay, great. What?
Any anticipation on how dark energy survey or LSST might help out your study?
Question. Can you repeat it loud?
I cannot. Yeah, sorry.
So the Dark Energy Survey is online now, adding a ton more objects to our catalogs, and then the Large Synoptic Survey Telescope will go even further. Any idea how those surveys might expand or better improve your study here?
Well, the dark energy goes more in the halo. Since we are taking a look at the disk and halo, it could be important. Yeah, for sure. I'm not so sure which or what they're taking in reality, because dark energy is something that we still don't understand quite well. But yeah, it would be great if we can know some sources and they say, well, we have some catalogs here in this area, because that's mainly in the halo. So since we are taking photos from the halo, so it's important for that part.
Other questions? I'll ask you a question. What was the hardest thing you found when trying to map this to Spark, the biggest engineering challenge?
I think that was to find the minimum distance between the 2 points. So reality is that I can use joins, and I can have one catalog here, another catalog, and then join them. But then, since it's a mathematical problem, so I have to find basically the points in between. I have to find a distance, and that distance has to be matched in mathematical way. And Spark in reality doesn't have that functionality if I want to join this catalog with this catalog in a distance. So what I had to do is round the numbers based on the rounding, try to match them. Once you match them, so now I find the distance, and based on the distance, I filter only the sources around the dot or the source that I want, and I get, let's say, 5, 10. And based on that, I get the minimum distance in that grouping. That's why I do the grouping, and in the grouping, I do some, well, not loops really, but then I try to find the minimum between the two.
And that's, I guess, to avoid the n-squared Cartesian join?
Yeah.
Makes sense. Any other questions? Then please join me in thanking Jose here and giving him a round of applause.
Thank you.
So our